So we've already seen one example of a non-constructive proof of an existence statement. And the kind of traditional next example to look at is the following. Show that there exists irrational numbers x and y such that x to the y is a rational number. And this is a very classic non-constructive existence proof. In fact, both Rosen proves it, as well as it's covered in the book of proof, as well as that other textbook, How to Prove It, that's mentioned in the syllabus. So it's covered multiple times, so I'm actually not going to consider this example right here because there's multiple places that you can go and read it if you are interested in. However, let's consider the following kind of non-constructive existence example. This is called Wilson's theorem. So this is what Wilson's theorem says. N is a prime number, and here I'm using the shorthand for if and only if. When dividing n minus 1 factorial by n, you get a remainder of n minus 1. So the cool thing about this is that this proof is a primality checker and a composite checker, or a non-prime checker. Because it's an if and only if statement, you know that if you take a number, take n minus 1 factorial, divide it by n, and you get a remainder of n minus 1, you know for a fact that's a prime number. If you take an n, you take n minus 1 factorial, you divide it by n, and you don't get a remainder of n minus 1, you know for a fact that that is not a prime number. So the proof of Wilson's theorem is actually a non-constructive existence proof. So it uses modular arithmetic, which we're actually going to cover later on in this course. So I'm not actually going to prove Wilson's statement. All I'm going to say is that it's a non-constructive proof. So how is this actually an example then of a non-constructive existence proof? Because I want to draw out a distinction and a point between constructive existence proofs and non-constructive existence proofs. So let's go ahead and check out Wilson's theorem and try a few examples to see how it works. So let's go ahead and try a couple of different n's, shall we? So let's go ahead and take n equals 3. So if we take n equals 3, and I want to use Wilson's theorem to check whether or not that's a prime number, it says that I have to divide n minus 1 factorial by n and check what its remainder is. So we have to pull out our old grade school arithmetic here to be able to apply Wilson's theorem. So what I'm going to do is, in applying Wilson's theorem, I need to divide 3 minus 1 factorial by 3 and check out what its remainder is. Well, this thing right here is 3 minus 1 factorial, that's 2 factorial, that's simply a 2, right? So that's a 2. Well, 2 divided by 3, well, that would be 0 with a remainder of 2. And if you notice that the remainder here, that 2, is indeed equal to our n minus 1. So yes, indeed, Wilson's theorem here tells us that yes, n here is prime. Because after dividing n minus 1 factorial by n, I get a remainder of n minus 1. And we can check out another example like, let's say n equals 4. So Wilson's theorem tells us that we're going to have to divide 4 minus 1 factorial by n, which in this case is 4. And so this thing here is, well, 4 minus 1 factorial, that's going to be 3 factorial, that's going to be 6. So we have 6 divided by 4, and yes, this is grade school arithmetic. 4 goes into 6 one time. I put my 4 here, I do my subtraction, I get 2, and I get my remainder of 2. And you'll notice here that this remainder of 2 does not equal 4 minus 1. And so Wilson's theorem tells us that since we did not get a remainder of n minus 1, that means that n equals 4 is not prime. It means that it's composite. So the really important thing about this is, well, it's very nice to be able to have a theorem that's checking whether or not a number is prime or composite. You'll notice very distinctly that Wilson's theorem here, if it tells you that a number is composite, it doesn't actually tell you what any of its factors are. And if you know anything about cryptography, and we'll cover some cryptography later on in this course, you'll know that factoring very large numbers is a cornerstone of cryptography. And so it's very nice to, if you know that a number is composite, to be able to find what its factors are. So Wilson's theorem, since it's non-constructive, it'll tell us, oh, your number is composite, but I have no idea what any of its factors are. And so we can actually see this in action. So what I'm going to do is I'm actually going to code up Wilson's theorem over here. So I have a function, Wilson is prime, and what that's going to do is just going to implement this particular theorem right here. So what I'm going to do is when I'm given an n, I am going to first off look at what my dividend is supposed to be. So that's this little bit in here. So I have to compute n minus 1 factorial. And then I take my divisor, which is n here, and I go ahead and I look at my remainder. And when I look at my remainder, all I have to do is check and see whether or not it's equal to n minus 1. And if it's equal to n minus 1, then Wilson's theorem tells us that it's prime, and this function can return true. Yes, that number n is prime. However, if the remainder is not n minus 1, then Wilson's theorem tells us that no, it is not a prime number. And so after that, I can make a little main function right here to basically give a command line interface that will tell us whether or not the statement, the number or the statement n is prime is true or false. And so you can go ahead and take this and you can run it. You can run Wilson's is prime here using this theorem, and you can check it. And if we plug in 5, you'll see that, yep, it returned true. 5 is indeed a prime number. You can plug in 6 to this thing, and we see that, oh, 6 is not a prime number, it is composite. And we could try this for some other really large number. So for example, let's try it on the number 295,927. So if we plug it in on that number, it's going to take a little bit. This is an inefficient algorithm because calculating the factorial of that number minus 1 is going to take a while. But in any case, it returns back false. Ah, that number is not a prime number. But since this is a non-constructive proof right here, it has told us that this really large number, 295,927, that thing is composite. But it didn't actually tell us what any of its prime factors are, or what any of its factors are for that matter. And actually, I know, because I constructed this particular example, that the factors of this number is 541 and 547. And I can go ahead and check that. So what we can see is that this theorem, because it's non-constructive, it's still very nice. It's still a true theorem, and it's still useful in some instances. But because the proof is non-constructive in nature, it can be less useful in some instances. So, while I'm not saying that non-constructive proofs are not useful, they are indeed useful. they're a little bit less nice because you can't get your hands on whatever it is that satisfies the statement that you're trying to show. So in the previous example, when we saw a constructive one, you can actually construct an example. Here, with this Wilson's theorem right here, it'll give you an answer of true or false, but since it's non-constructive, it doesn't actually give you any of, in this case, the factors of a number if it turns out not to be prime. So on the one hand, constructive proofs, they're nice. They give you something that you can actually get your hands on because you actually constructed it. Non-constructive proofs, on the other hand, they are indeed theorems, but since you didn't actually construct the number, you're not going to be able to use it in any further sort of analyses. So that's the main reason why I wanted to show you this example right here, is basically to show you, compare and contrast the difference between constructive and non-constructive existence proofs.